नमस्कार दोस्तों, वेलकम टू गेट वाला। मैं हूं सतीश कुमार दुरिशेट्टी, फैकल्टी ऑफ मेजरमेंट्स। मैं आप सब लोग को यहाँ स्वागत कर रहा हूं। जितने लोग लाइव में हैं मुझे एक बार वॉइस कंफर्मेशन कर दीजिए, ऑडियो वीडियो सब कुछ क्लियर या नहीं। आज हम डिस्कस करने वाला है, वी आर गोइंग टू डिस्कस द आईएएस मिशंस, सॉरी आईएएस मेजरमेंट्स। ओके, आईएएस मिशन में मेजरमेंट्स का सब्जेक्ट का मेंस क्वेश्चंस वी आर गोइंग टू डिस्कस। सो टुडेस क्लास we are going to discuss about the data acquisition system. So data acquisition system, today's class we are going to discuss about data acquisition system. So this was a question which is very frequently asked for both electrical and EC students. Okay, so question, just note down the question. This was one of the previous year question. Explain data acquisition system. Explain data acquisition system with any two examples. So sometimes this question can be asked for 12 marks also. Okay, so what is data acquisition system? So first of all, you should write data acquisition. What is data acquisition? How to define the data acquisition? How we can define the data acquisition? So what is data acquisition? So how to define the data acquisition? It is a process of achieving the information of a physical variable in required format. So the required format can be analog or digital. Okay, so the physical variable means it can be temperature, it can be pressure, it can be strain, etc. Okay, so there are two types of data acquisition systems, my dear. One is a There are two types of data acquisition systems. One is the analog, other one is the digital. So there are two types of data acquisition systems. One is the analog data acquisition system, other one is the digital data acquisition system. Analog DAC system, digital DAC system. Okay, so we'll see in detail now. For example, I will give an example of strain data acquisition system. Data acquisition system for strain measurement. DAC system for strain measurement. Okay, data acquisition system for strain measurement. So please note down how it works. Okay, so this is our cantilever beam. So for this cantilever beam, we are having certain length, and this is the breadth. So this is a cantilever beam. So what we call this as cantilever beam. So on this cantilever beam, you are keeping the strain gauge. So this is a strain gauge. This cantilever beam is kept in a Wheatstone bridge. All the resistors are equal in the beginning, and this particular Wheatstone bridge output is connected to differential amplifier, the plus and this is a minus, and then after it is given to ADC. That ADC will convert into 7-segment display. So here comes okay. So this is the operational amplifier. This is the ADC. Here comes the V0. Here comes the V bridge. हमको ये पता है this V bridge can be taken as Vs by 4 into delta R by R. Okay, so this is how a measurement system is developed. This is how a measurement system is developed. Please make a note of this picture. So this is an example, best example for the strain data acquisition system, how to measure the strain that is given here. Chalo, how it works. So first of all, you should understand what is strain, how it works. First of all, you should understand what is strain, how it works. When no stress is applied, at that moment, this length of the cantilever beam is nothing, no change, and the length of the strain gauge also no change, and the resistance also unchanged. So now when the force is applied, then what happens? If you see, this cantilever beam bends, and the cantilever beam bends, now this particular also expands. When it expands, it will be L plus delta L here. This will be L plus capital delta L. This will be R plus capital delta. So now if you see, the quarter bridge expression is this. So what are the various blocks present here? If you check clearly, first of all, we have a cantilever beam. On the cantilever beam, there is a strain gauge, and the strain gauge is connected to Wheatstone bridge. Wheatstone bridge is connected to ADC, or sorry, op amp. Op amp is connected to ADC. Then comes the display. So see here, various blocks. So this is cantilever beam. Next connected one is strain gauge. Next connected one is the Wheatstone bridge. Next connected one is, this is Wheatstone bridge. After that, it is connected to operational amplifier, then analog to digital converter, and here comes the 7-segment display. Okay. So for this cantilever beam is called as sensor, strain gauge is called as transducer, and this entire system we can call it as signal conditioning blocks. So what we call this as, this entire system is called as signal conditioning circuit. Okay, then finally comes display. So these are the various blocks of signal conditioning. Signal conditioning means which is a combination of many analog circuits. It can be Wheatstone bridge, it can be op amp, like that. Okay, so this sensor plus transducer plus signal conditioning circuit plus display is called as DAC system. So this is the blocks of the, what we can write, blocks of DAC system for strain measurement. That's how it works. And here comes the stress. The stress is converted to strain, and that strain is converted to here, and here comes the strain del R by R. So this is our del R by R, and here comes the Wheatstone bridge. Got it? So this is how the various blocks of the data ECMO system will work. Chalo. So if you see now, this is a data ECMO system for the strain measurement system. So if you see the strain gauge converts the mechanical strain to electrical strain. So if you see the strain gauge, this strain gauge is converting mechanical strain to electrical strain. It converts mechanical strain to electrical strain. Mechanical strain means delta L by L. Electrical strain means you can say delta R by R. So now from this I can write the gauge factor is equal to this by this, electrical strain divided by mechanical strain. So this is what our gauge factor, del R by R by del L by L. Okay, so this is one data acquisition system for the strain measurement. So now I will go for another example. Data acquisition system, DAC system for temperature measurement. For temperature measurement. So I will go for temperature measurement. So how the temperature can be measured? Okay, so two examples. So for temperature measurement, we are using a transducer that is called RTD. So this is a RTD. Okay, so this is kept in hot water bath. So is here the temperature is changing from 0 to T degrees Celsius. Then its resistance also will change. So this is plus minus, this is a Vs. This is R, this is R, this is R. And here comes again the same concept. Once the bridge voltage comes, that we can connect it to the operational amplifier. Op amp output is connected to ADC. ADC output is connected to the display. So this is plus minus. So this is operational amplifier. This is the analog to digital converter. So this is what we call as 7-segment display. Got it? So please note down. When the temperature changes from 0 to 3 degrees Celsius, here the resistance is going to be changed as R plus delta R. So what are the various blocks present here? If you check the various blocks, here also we're having the RTD. We're also having the RTD. So this is RTD, and RTD output is connected to Wheatstone bridge. Wheatstone bridge output is connected to op amp, ADC, 7 segment display. So here if you see, this is our temperature, like this it is changing. This is the temperature. So this is RTD. This is a Wheatstone bridge. Okay, so this is a Wheatstone bridge. Then it comes the op amp, ADC, and here we are going to get the 7 segment display. Okay, so this is what we call as sensor. Have you seen again the same model? So this is the transducer. So this is the temperature transducer, thermal transducer, temperature transducer, which gives me some change in resistance, Wheatstone bridge, operation amplifier plus ADC plus display. Okay, so this is a data diagnosis system for the temperature measurement. Here actually what is happening, when the temperature is changing from 0 to T degrees Celsius, the R0 is changing from, resistance is changing from R0 to RT. So this RT is given as R0 into 1 plus alpha delta T. So now if I am changing this, this is R0 plus alpha R0 delta T. So this is a RT. So RT minus R0 is equal to alpha R0 delta T. Okay. So now if I am changing this change in resistance by change in temperature into 1 by R0, that is the alpha. So which we call as temperature coefficient of resistance. Okay, which we call as temperature coefficient of resistance. As the temperature increases, resistance also increases. So this alpha is treated as plus 0.00392 per degree Celsius. That is for platinum. Okay, so these all are temperature data systems. Chalo, next question for the IES. I can go for, what are the various measurements we can do with Q meter? So this is also IES questions, my dear. Next question, IES question, explain the applications of Q meter. Explain the applications of Q meter. Applications of Q meter. So what are the various measurements that we can do with Q meter? So some topics which are very rarely covered in the GATE examination, sometimes GATE में बहुत rare में आएगा, so those topics can be framed for maximum marks in IES descriptive paper. Why? Because Q meter is such a topic, data acquisition is such a topic, digital voltmeter is such a topic. Okay, so miss मत करना these topics को. TIPAMO, DAC means What is DAC? So this is the DAC. So you're asking about the DAC now. So this is the data. Data acquisition means this. So what is data acquisition? I was telling. DAC means data acquisition. How you are acquiring the data? It is a process of achieving the information of a. It is a process of achieving the information of a physical variable in a required format. It is the process of achieving the information of physical variable in the required format. Either it is analog or digital. In a required format, if you are achieving, then that is what we call as data acquisition. So there are two types of data acquisition systems: analog data acquisition system, digital data acquisition systems. I have given the examples for it. So one is the data acquisition system for strain measurement. I have given. Next, data acquisition for the temperature measurement in the industry. How you are going to measure the temperature? So this is a RTD actually. What we call this as a RTD. So this is the steel rod. So this is a steel, and for which we are achieving the platinum coating. Platinum coating. Okay. So platinum, as a platinum, this particular RTD works on. RTD means this RTD. This RTD means this is what we call as RTD. RTD means resistance temperature detector. As the temperature increases, resistance also increases. That is a resistance temperature detector. Okay. So these are the various blocks. Now आज और एक क्वेश्चन मैं क्या एक्सप्लेन करना चाहता हूँ सर, Q meter, applications of Q meter. So Q meter is used for what measurement? Q meter is used for Q factor of a coil. It is used for measurement of Q factor of a coil. Next, it is used to measure the dissipation factor. It is used to measure the inductance of a coil. It is used to measure the effective resistance of coil and distributed capacitance of the coil. Resonant frequency of the circuit also it is used. So these are the various measurements it can be useful for. So first of all, what is a Q factor? Q factor is defined as 2 pi into energy stored in a cycle by 2 pi into energy dissipated. For a coil and for a capacitor, we are going to have a Q factor. So Q factor ka coil omega L by R, Q factor capacitor 1 by omega CR. Okay. So if you take a coil, coil should have a maximum storage capability. If you take a capacitor, the capacitor also should have maximum storage capability. But sometimes what happens, practically it is not possible. There may be some dissipation also. So if you take a coil, so if you compare its capability of storing energy to the dissipating energy, then we are going to get this expression. Or simply speaking, Q factor of a inductor can be taken as voltage across inductor to the voltage across resistor omega L by R. This is measured by the Q meter. Similarly, Q factor of a capacitor. Q factor of a capacitor can be taken as 1 by omega CR. So Q is equal to VC by VR if you take 1 by omega CR. So these two parameters are measurable by these things. So please note down, for a best coil, the Q factor should be better so that its energy storage capability will be better. If you see the Q meter, so this is a circuit of the Q meter. So this is a circuit of the Q meter. So if you see the circuit of the Q meter, there will be oscillator. To that oscillator, we are having a shunt resistance. Across the shunt resistance, we are weighing the voltage. So that voltage we call it as thermocouple voltmeter. So this voltage is measured by the thermocouple voltmeter. Okay, and here comes the coil. So this coil is having terminals. It is connected here. Remember, the coil is having resistance also, and between the turns there is a distributed capacitance also, because current entering and current leaving through the turns, which creates certain charging and discharging concept, which causes the distributed capacitance. And in addition to this, there is another one capacitor called tuning capacitor is kept. Okay, so this tuning capacitor across, we are going to have electronic voltmeter. So these are shunt resistance. Across the shunt resistance, we are going to get the voltage. Here, this oscillator is going to set at radio frequency. Why? Because resonance condition has to be achieved. That resonance condition is going to be achieved at a particular frequency, so that in a RLC circuit, the inductive reactance and the capacitive reactance both are going to get cancelled to each other. Why? Because as the frequency is increasing, the reactance, inductive reactance XL, which is omega L, as a frequency is increasing, XL also increases. Xc is equal to 1 by omega C. As a frequency increasing, Xc decreases. So when this XL is equal to Xc at a particular point called resonant frequency, there is a peak point comes. So that point is a point at which resonance is going to be achieved. Got it? Chalo. So now what we will do, we will set a frequency. At resonant frequency, if you check the voltage across a capacitor EC, voltage across the capacitor and voltage across the applied voltage, if you see, that is equal to I into Xc, and this is I into R. Why? Because at resonance this E becomes IR. At resonance this circuit purely becomes resistive circuit. So this EC by E is nothing but Q, which is the 1 by omega CR. Am I right or not? So this is the EC by E, we can call it as. So Q is equal to, so voltage across a capacitor by voltage resistor is equal to Q. That's how the Q measurement is done. So that means, how to understand the circuit has reached the resonance? If you keep the electrostatic voltmeter here, the electrostatic voltmeter has to sense a highest voltage. That highest voltage should be Q times of the E. Got it, my dear? So that's how it should work. Chalo. Done? Okay. So that's how the Q measurement is done. Next concept is digital voltmeter. Next question. Next IES question I'm taking. Next IES question I'm taking. Explain the DVM working, digital voltmeter working, and resolution of 3-digit, 3.5 digit, 3-digit and 3.5 digit. Okay, make a note of these points. Chalo. So now if you see, actually we don't have any digital voltage. So we don't have any digital voltage. So analog voltage is going to convert into digital. Analog voltage is going to convert to digital, and that digital is measured by the display. That digital is measured by the so this is the ramp type DVM. These are the types. These are the types of DVM. But majorly the context here is the 3-digit and 3.5 digit. Chalo. So now if you see the 3-digit DVM, so this is a 3-digit DVM, my dear. So what we call this as 3-digit DVM. So this is the 3-digit display. So this is a 3-digit display. So what is a 3-digit display? So in the 3-digit display, we're having positions like this: A position, B position, C position. Okay. So this is full digits changing from 0 to 9. This also 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 changing here. What is the position? The position can be here. The position can, that is a switch actually. Position selection is a switch. Okay. Position selection is a switch. See, for example, if the position selection switch is here, then I am going to get dot 0, 0, 0, 0, 0, 1, 9, 9, 9. So total counts are 1000. How many counts? The total counts are 1000. Okay. So the minimum value is 0.000, the maximum value is 0.999. That means 1 volt. It is how much? 1 volt. So the range is 1 volt, and the least increment that it can sense here is equal to 0.001. That means that is 1 millivolt. Next. So suppose if the position selection switch is here, that means 0.00. So here comes 3-digit na, 3 digits. So 0.00, 0.001, 9.99. So the numbers will change from 0 to 9. So the total counts, if you see, 0.002, 9.99. So the total range is 1000. Total range is 1000. Why? Because, sorry, total counts are 1000 because starts from 0.00 ends to 9.99. So total counts are almost like 0 to 999 and 1000 counts. But if you see the range 0.00 to 9.99, that means the range is 10 volts. Okay. So what is the minimum increment it can detect now? 0.01. That is nothing but 10 millivolts. So this is 1 millivolt. This is a 10 millivolt. Next, similarly, with the position selection switch is here. If the position selection switch is here 0, 0.0, 0, 0.1, 99.9, so 99.9, so that is 100 volts. So 0 to 100 volts. So the resolution will be 100 by 10 power 3, 100 millivolts. Okay, so please make a note of this. Any doubts? Position selection switch is not given, we can go for 1 by 10 power 3. So that is a count. So now if you see the resolution of a digital voltmeter, that is 1 by 10 power n. Resolution in a selected range, if you see, resolution in a selected range, if you see, that means 0 to 1 volt, 0 to 10 volts, 0 to 100 volts. So selected range by total counts. Okay, selected range by total counts. So now if you see this, the 3-digit display, if you see, resolution of DVM is 1 by 10 power 3. That is, if the position selection switch is not given, we can tell it directly 1 by 10 power n. But if your position selection switch is given over range of 1 volt, the maximum voltage by maximum current you have to take 1 volt by 1000, that will become 1 millivolt. That's what I told you. Over a 10 volts range, 10 by 1000, that becomes 10 millivolts. For a range of 100 volts, it becomes 100 millivolts. Okay, that's what. Now I am going for 3.5 dBm. 3.5 dBm means what? 3.5 digital voltmeter. That means in this we have 3 full displays and 1 half digit. So this is 3 so this is 0 to 9 and this is 0 to 9. This is 0 to 9 and this is 0 to 1. Okay, so the range here is 0 to 9 and this is 0 to 1. Got it? So point 0.000 to 0.999. So here these are the full digits, these are the half digit. So full digits means 0.000 to 0.999, so the 1000 counts. And here this is 1.00 to 1.999. This is again 1000 counts. Why? Because the half digit is there now. That half digit can change between the 0 to 1 only. So 0 to 1 only it can change. The total counts are 2000. So counts will be doubled, and the range also, if you check, it will change it from, suppose if the position selection switch is here, then 0.000 to 2. So it will go for 2 volts. Got it, my dear? So note down. Chalo. So now if you see the resolution won't change. The minimum increment that can detect here is, what is the resolution? Resolution means the minimum increment it can detect. So the next increment is 0.001 ना. So resolution में कुछ भी change नहीं आएगा. Good evening. Resolution में कुछ भी change नहीं आएगा. So resolution क्या होगा? 0.001 होगा. So 0.001 होगा. So total counts are 1000. This total counts are 1000. So total together 2000 counts are there. Okay, that's it. Next, suppose if you are taking the range, but if you see the range, how the range is going to be changed. So if you are taking this 3 digit, so if you are taking 3.5 digit, if you take the 3.5 digit, how it will change? See here, this is a 3.5 digit. If you take the 3.5 digit, how it is going to be changed? So for the 3.5 digit, this is 0 to 1. These are changing from 0 to 9, 0 to 9. Okay. So 0 to 1 volt, if you check now, 0.000. So this is 0.002. This is going to be 0.99. So this up to this. Next 1.00 to 1.9 and another one. Okay. So now if you check the resolution, so this is a resolution of 3.5 digit. This is a resolution of 3.5 digit. Resolution of 3.5 digit or range of 2 volts. That is a maximum volt by maximum counts. So here the maximum voltage is now not 1 volt. The maximum voltage is increased to 2 volts. Why? Because this half digit will be giving up to 0.999 and this half digit will be giving 1.999. Okay. Got it, mere doston? Got it? Chalo. Similarly, I can go for range. 10 volts will extend it to this one. If the result position selection switch is here, if the position selection switch is here, like this, 0.00, 0.01 to 9.99, 10.0, 19.99. So 0 to 20. So if you select the resolution selection, so here resolution of 3.5 digit over range of 20 volts would be 20 by 2000. So maximum voltage here changing from 0 to 20. 0 to 20. So 20 by 2000. So answer is 10 millivolts. Got it? So next here. So these are the various things, my dear. If you have any doubts, you can ask me with respect to this DVMs. We have discussed the quality questions. Any other doubts? So what are the topics we have discussed? We have discussed the data acquisition system. We have discussed data acquisition system. We have discussed. Then we have also discussed digital voltmeter. Sorry, we have discussed the Q meter. Next, we also discussed the DVM. In DVM, we have two categories. We have two categories. One is the 3-digit DVM, 3-digit display. Next one is the 3.5 digit display. And we also covered resolution. That okay. If you have any doubts, you can ask me, my dear. Anybody is having any doubts till that? Anybody is having any doubts? Let me know. Enough for today. I'm closing.